Okay, now sticking with the theta equals 0 case, although I've given you a good hint down here as to how you can solve it if theta isn't 0. And one other thing I'll note down here. The frictional force will be less than mu k mg because the normal force is going to be less than mg. Okay, since the normal force is less than mg, so you got to take that into consideration. And I really do just recommend that you go ahead and work out that case. It'd be good practice, including free body diagrams and large enough graphs that you can actually estimate slopes. I'm getting graphs this big and people telling me they have the slopes. I don't believe it, okay? And I'm not going to believe it on the test. You know, do graphs that are big enough that you can make inferences if that happens to arise, and there's a good chance it will. Okay, so we have this. Well, that's V0 for the projectile. So let the edge be the origin. Then and I'm just going to indicate the coordinate system. Usually you want to use a right-handed coordinate system, but in this case it doesn't matter. And this is still a right-handed coordinate system, x-axis, y-axis. Okay? With respect to this coordinate system, I choose to set up your position function r of t is going to equal I've run into another notational glitch, or something I have to revise in the notation, because I really want to have an initial velocity and a final velocity for my projectile. But I can't call the final velocity VF because I used VF up here. Okay? Well, I'm going to say, okay, I'm going to call this VF2. Haven't written it that many times, it's easy to put a 2 on it. For the final velocity of phase 2. Okay? So let's just label this phase 2, and I'm going to call that final velocity of phase 2. And I'll use V sub I instead of V0 for the projectile. I'm even going to change that. I'm going to call that VI3. initial velocity of the projectile, or actually initial speed. Let's it's not a vector. And I want to call it the initial speed because you know that if you modify this for an angle theta on the ramp, then you're going to have a horizontal and vertical coordinate of this thing, component of this thing. So you're going to want to regard that as speed, not the velocity. Okay. So anyhow, we'll call it VI3T times I. That's your horizontal component of the motion, plus one half GT squared J. Since I've got my coordinate system rotated 180 degrees, the positive y direction is down, so that is plus. Okay? So there's your R of t function. And we want R of TF, final time for the third phase, to equal XI plus HJ. Okay? Now this is assuming we know X, but we're going to get relationships one way or another that help us pull us all into one whole here. So your initial velocity times your time for the third phase has to equal X, and one half GTF3 squared has to equal H. From this, it's supposed to be a T, not an F. It's such a pretty F too. TF3 is then going to equal the square root of H over G, okay, and that implies that X is going to have to be VI3 times the square root of 2H over G. Well, that equals what? VI3 is VF2. And these aren't just symbols. I mean, what's this mean? This is your initial velocity for the projectile. This is your final velocity for stage 2, or phase 2. Okay? And that's noted here. I don't have room to write it there. This is equal then, well, there's VF2. It's going to be this final velocity for stage 2 times this, and of course it's a square root times a square root, so you can multiply through, and you get this. Oh, there's h. Okay. I was hesitating there because I just had these 3 terms and I knew that that had dimensions of distance, so that this, you'd be doing a square root of something with dimensions of distance, which wouldn't give you distance, which is what x should be. So I knew there had to be something else there, but it wasn't an L squared. So what was it? Well, I just didn't write the h. And it's 4 times that. Okay? And what about the dimensions here? Okay? Energy over weight. Okay? Are the dimensions correct? Well, no, because I didn't write the stupid h in here either. Okay? And now the dimensions are okay. If you just think in terms of kilogram meter squared per second squared, kilogram meter squared per second squared times meters gives you kilogram meters cubed per second squared. You divide that by kilogram meters per second squared, you get meters squared. So now you got meters squared here and meters squared here, and it all works out. And then you can factor out that square root of 4. And I'll keep these terms. I could factor an h out of these terms, but there's no 4 there. But it's kind of easier for me at least to look at if I've got the h there and there, because then I can easily compare units, but it'd be easy the other way too. Okay, so there we have it. Now, our goal was to relate the 5 or 6 quantities that we started with, which were, well, let's see what quantities we've got related. We've got x, and I'll repeat that here, x equals then this. So we've got x, that's 1, m, that's 2, initial PE, that's 3, h is 4, UK is 5, and L is 6. Those are all different. And if I look at my original list, there are 7. So what am I missing? Oh yeah, A naught. Okay, well, A naught is related to your initial potential energy by the graph. Okay? So we could say this is 2 times the square root of potential energy of A naught, where potential energy is regarded as a function of A naught. It's function notation, not multiplication, okay? So, okay, well that relates everything but theta. But theta was 0. This is the theta equals 0 case. So now if we want to really have fun, we go back and multiply this. We change this to a non-zero theta. Now this part isn't bad. You just have to take the potential energy change and change it slightly because you have a decrease in gravitational potential energy now. But this is going to be less fun because now you would have a VI3 cosine theta and a VI3 sine theta in here, okay? This would be VI3 cosine theta, and then you'd have a VI3 sine theta times T in addition to this. So it gets a little uglier, but more powerful. Okay, this equation, without the theta in it, can pretty easily be solved for any of these variables. You want to solve for L? That means you know the angle, you know the height, you know the mass, you know the potential energy, you know, well, you got the height again, and you know X. If you know all those things, you solve for L. You just square both sides, take the term you get from here, slap it over the other side, divide through by mu kh, and you got L. Okay? So this relates everything. This solves the entire situation, provided you know, well, provided theta equals 0. Okay, provided you got a level ramp. Now you throw a big old wrench into the works if you throw theta in there. Not a huge wrench, but it's a big enough wrench that it gets a little bit confusing to do the algebra, depending what you want to solve for. Okay, and you might think, yeah, what if I did get evil between now and then? I mean, more evil, and choose to not give you X down there, just give you, let's say, the kinetic energy when it hits. Okay, whole thing could still be analyzed. I probably wouldn't want to take that much time out of a test, because I think if you could do this, that's A work. Okay, if you can break a problem down that far and then solve the individual parts, and even if you make a mistake or two like you never see me do, as long as it isn't a big conceptual mistake or such a bonehead algebra mistake that the fact of the error is so obvious it slaps you in the face if you're paying attention, then it would still be A work, okay? Or could still be A work, depends on how bad you do with the algebra, because you got to do the algebra. Okay, well, I'm going to cut the camera here.